Okay, perfect. Good afternoon. So we figured out how to transmit 100 kilobits per second. So we will talk about terabits today. My name is Hans-Juergen Schmidtke. I try to take care of the network hardware engineering team at Facebook. Facebook, probably most of you heard, consists of several businesses. And those businesses create actually a lot of demands. And here are some key figures. You find a lot more online, but I like to point some of those out here. Receiving 65 billion messages per day just gives you a little bit of a feeling of the scale we have to support, but also the availabilities we need to support. And clearly, text messages are much easier than when you look at another figure on the right side, when we have to actually transmit and receive and over our equipment more than 10 million broadcasts live on a single evening. What is a huge demand in terms of topology and throughput for our infrastructure. So in general, we support a lot of these applications through a lot of hardware. And this hardware requires a lot of sites. In this case, we have, in our case, we have announced 15 data center sites globally. And a site consists typically of up to 5, 6, and sometimes even more buildings. So not all of these sites are fully built out, of course. Some of them are still somewhat in the construction phase. But this gives you a little bit of an impression about the size and the scale we are dealing with and we have to work with to just support the demands from our community. And those sites are distributed across the world. So essentially, we're dealing here with a distributed architecture infrastructure at any time. And we've given also a lot of talks around distributed compute and storage. And it's not just inside a data center or data center building. It's also across the entire world. So with this comes demands for networking inside the data center, typically up to 500 meters, or across data center buildings, 2 kilometers. And as you can see, even up to thousands of kilometers across the world, as we need to support the connectivity between these sites. So network means a lot for us. Today, we're talking mostly about data center networks inside the data center. So the challenges, no surprise. There is a continuously exponential increase. Some people would at times even say super exponential increase in bandwidth requirements across several tiers. I like to point out that the machine-to-machine traffic is typically 10 times larger and grows faster than the machine-to-user traffic. And that's mostly driven by application like disk flash or east-west connectivity of new applications that are distributed inside the data center. And that drives the demand that we experience. And clearly, the workloads, and we submitted Zion or Yosemite Glacier Point accelerator modules this March at OCP, the workload demands are also increasing just on a rack level. So we were talking about AI, ML clusters. They impose demands. But also, when you look at some of the other applications, not just the sheer uptake, but the application, how we use them, requires a lot more bandwidth between racks. And when I'm saying between racks, I mean between any racks, inside the data center building, between buildings, in a site, but all across sites as well. So at the same time, our architecture, the Fabric 4 architecture, was limiting us somewhat to 3 buildings. We needed to make sure we actually have a lot more buildings at a given site. Plus, the limits of the previous architecture was around 100 terabits or hundreds of terabits between those buildings. So we run here continuously against a threshold we needed to expand. And this pressure coming literally on this architecture we have had for a couple of years now comes from different sides, from the rack side, from the demand side, coming from the users. But also, when you look at the new clusters and applications we need to support, so we literally have an architecture in place that really didn't meet any of those demands anymore. So we had to, now AI and ML and others require a terabit or more out of a rack. And so we had to do something about it. Plus the fact that it was not easy anymore to just upgrade and make it faster. So what I'm saying is when you look at the typical switch chip throughputs, you can see that over the last years, the switch chip vendors have done actually a pretty good job to scale up by factor 2 every 2 years, what you would kind of expect in the old Moore-Laws fashion. But then at the same time, the I/O didn't speed up as fast as we wanted to. And then the optical vendors, in return, did not deliver as fast and at scale as we needed. So when you look at this table, when you look at the throughput, the SerDes speed, and the ideal optical speed we would have liked to see, you can see that the actual implementation is lagging behind. So the optical vendor landscape is not delivering what we needed. So you can see we couldn't just upgrade the old architecture, but just scaling up. So this is nearly like one of those engineering principles and questions. Are you scaling up, higher speed, or are you scaling out? In this case, more fiber. And so we're running, in addition with this, what we see right now happening in the market, into a power limitation in the outer years that is actually pretty severe. So we have a lot of challenges to solve for. Bandwidth demand, power, the scaling up doesn't work as much as we wanted to, and we see a lot of applications right now pushing pretty high capacities. So what did we do about that? We announced in March that we do what we call F16, Fabric 16, and H-grid. And I'm explaining now what that means. Fabric 16 is essentially a 16-plane architecture. So we moved from 4 to 16-plane architectures, and that increased the also the capacity that we could get out of a rack, so up to 1.6 terabits per second. And implicitly here, I'm assuming that we still stay at 100 gigabit per second speeds per fiber pair. That, and I show that and illustrate that in a moment, also helps us to optimize the number of chips. And that allows us to have much better power and space. So we could now use the 100 gig CWM4 OCP optics, pluggable optics, and continue to use it. We use it now for a couple of years. It's ramped up. It works well for us. And we could now extend the lifetime of this optics as well. So what does it mean when you look and click deeper? Essentially, what we've done is we went from a 4 times 128 port architecture, multi-chip architecture, 400 gig fabric. You can see here the FSW consisting actually out of 2 layers, into a 16 times 128 single chip 100 gig fabric. And that's illustrated on the right, where you can see the topology. The topology becomes flat and scaled out. And in this next slide, actually illustrates what it means. It's always good to look at architectures from the bottom up, in the sense of what is the life of a packet? Where is it created, and where is it being transmitted, where is it switched? And the idea is really to optimize that so that you have the minimum amount of switch events and handlings and the minimum amount of IOs. That's where the power and the cost is hidden. And so you can see on the left side is the old architecture, where you could see that a packet would have been handled quite often along the way. You can see literally 9 hierarchies, starting from the top of rack up to the fabric, spine, edge switch, into the FA. And of course, if you count the hops and back. And so on the right side is the new architecture that is flat and scaled out, and it is significantly reduced. In addition, we were able to eliminate a whole tier. That's the so-called edge switch tier that we had in the old architecture. So not only we scaled out and reduced the number of hops, we also were able to eliminate a whole tier. All of this is leading to significant power savings for us, far beyond just a new switch chip generation. And we are continuing to look at these concepts. I mentioned optimization of I/O across our entire fleet, of course. And as we look into architectures in the next years to come, this will be one of our guiding principles and philosophies to optimize for the lowest amount of hops and I/O connections. So what does it mean? So I mentioned before the old architecture was mostly limited to 2 to 3 buildings. Now we are connecting up to 6 buildings. But that also means in reality we need to come up with a new fabric architecture. And we call this new fabric architecture F16 inside the building. And then we need to come up with a new fabric aggregation architecture, FA, that we call H-grid. And in reality, this looks like a lot of fiber. And what you can see here that every big 16-plane F16 element is representing a building, it's inside a building, is now connected through the H-grid. And it allows us now to build a very efficient data center site where you essentially can now move applications across buildings in a given site with a very efficient H-grid connection between those buildings. So the underlying hardware is mini-pack. So the switch element is essentially consisting of a Tomahawk 3-chip 12.8T. It's a very modular architecture. You can see 8 line cards. We use mature, scaled-up, reliable optics, 100 gig CWM, 4 light optics. And all of this leads to what we believe very low power and small size. This is the key building block of the architecture of F16 and H-grid. And again, it's was part of the submission to OCP already in March. So we did a lot of learnings from an operational perspective, particularly keeping those designs very simple. So orthogonal direct architecture allows us direct mating. We also can now do field replaceable units. So it's very modular in terms of failure modes, and so it's really something it's like comes out of a learning from our Galaxy / earlier devices, where we also noticed that at times not the most complex devices tend to fail in the data center, but just some of the CPUs failed, and in comparison to the optics, of course, and the switch chip, typically and classically a much cheaper device, but was very sensitive to failures. So we have done some learnings, and so it becomes for us paramount to do some modularity and particularly around the SCM. So the guiding principles here for us and the philosophy we will pursue here is in order to move fast, we need to be able to do a lot of hardware abstractions. So SAI, as an example, becomes paramount so that we can ramp up and replace those hardware very, very quickly. We're also working increasingly on our testing capabilities, and also will share that moving forward with OCP, in terms of test automation and the way how we're testing and what we're testing. And this is really, for us, becomes a continuous, never interrupted deployment model. So the philosophy that I like to share here is, and as we build and have built Minipack, is we will expand on all these vectors. So key moving forward for us will be the packet optical strategy. We discussed that over the last years. The conventional pluggable optics is not scalable on the long run for power and cost and probably also reliability reasons. So there is the need to bring optics closer to the switch chip, and that will end up leading to what we call co-packaged optics. The idea here around co-packaged optics is to integrate optics as close as possible to the chip, and with this reduce the fairly expensive, because these are the most expensive heaters, copper lanes between the SerDes on the chip and the optics itself. We see that this approach, when you include retimers, can actually save up to 30, maybe 50% power, what is huge for us. So the other advantage we look at right now when it comes down to this integrated approach is improved reliability, much more scalable manufacturing. I mentioned we had issues scaling up any new optics, so we hope that this new approach can help us here. And of course, it needs to be also scalable for cost. What we're doing here is essentially spearheading an approach of improved I/O. Input, output, edge of a chip. That means we're starting with network because that's where the highest packet density is, but it will not end here. Next, probably accelerators and then GPUs and CPUs, just because of the I/O increases expected over the next years. So it becomes more a matter of timing than if we do it or not. So moving forward, we are not just solving for networking in this particular tier, but also for a much wider industry. And that is important because we try to build ecosystems and not do it in a way that is singular to one company. That's why we founded together with Microsoft JDF that we called co-packaged optics. We are submitting and publishing altogether 3 documents in the next weeks. One is already released. That is about the discussion document about optical modules. We also will do and publish in the next weeks co-packaged optics assembly technical guiding documents, as well as optional external light sources that we see here as a way of fulfilling the design requirements. So if you're interested in those documents, please send an email. It's listed here, or just contact me directly. So Microsoft and us are pursuing and trying to guide and lead this industry in this direction. Again, we view this as a first step among many as we solve for the I/O problem of those chips. And clearly, the chiplet interconnects that were mentioned here today before play a huge role as well. So the theme here is a single company can't innovate it all alone, but so can't a single open optical body either. So there is a collaboration announcement that was already given this morning between OCP and Telecom Infrastructure. Both TIP as well as OCP pursue open goals, have very similar cultural principles, and I think are very, very important bodies to collaborate with. So the idea is really here to enrich both optical, the open compute project, as well as the telecom infrastructure project by much closer collaboration. And to this extent, EdgeCore announced that they're going to submit their DCSG, the disaggregated cell site gateway, to OCP as well. That is essentially a switch. When you look at the commonalities from a hardware perspective, a lot of switches and are essentially also routers could be used from an OCP perspective in TIP. And TIP, as you just heard, can reuse and use a lot of those elements in much bigger, different telecom contexts. So these both bodies are really, I think, it's a really win-win deal to collaborate together, and you will see and hear in the next years, I guess, a lot more about it. I am co-chairing the TIP Open Optical Packet Transport that includes also the DCSG, as well as the other packet optical, DWM, and switch chip initiatives. And I can see that there's a lot of good ground and common ground we can grow together. And I'm really looking forward to this collaboration. So in summary, I covered essentially reasons why we don't see that the technical supply doesn't really meet anymore the workload demands. And we need to do something about it. Of course, we need to continuously innovate on the switch chip level, on the packet optical level, on the chiplet level. We need to continue to innovate to drive up instead of just scaling out, because scaling out goes only so far. But for now, we were able to scale out and meet what we need. And that is called topology optimization. Essentially, in this case, means more fiber. And it allowed us to really do an architecture that is what we believe very resource efficient. We believe that also besides just scaling out and putting more fiber in there, in the next years there will be a lot more work that needs to be done, particularly on the packet optical side, to meet the demands that we foresee in the next years to come. And you're all invited to do so. We see an industry-wide implication. So we believe that the tech we are developing and the architectures, the topologies, the I/O concepts that we are developing are actually widely applicable, not just to one industry or one company or one data center provider, but rather also across many industries, from enterprise to the telco world. And so it is, for us, very important to invite many companies to this journey. And for sure, our collaboration with Microsoft on the packet optical, co-packaged optical side is also meant to unify the industry and lead the industry in a direction because we see that the industry very often becomes very fragmented and loses out. So very important to us to build these industry partnership, and then of course with OCP and TIP collaborating closely together in many aspects, starting with the data center cell side disaggregation data center, DCSG, the disaggregated cell side gateways. We see a very, very promising step to really have a win-win deal for much wider industry and audience. Thank you very much.